Hey guys, welcome back to another video. So in today's video we are going to see how we can compress this image with the help of k-means algorithm. But more importantly, we are going to understand and visualize in detail that how we can make this process 123 times faster with the help of some really cool math concepts. So the performance is comparable to a task taking 5 minutes versus more than 10 hours. So if you are somebody who is wondering and whether you need to understand and learn math to become a good machine learning researcher or an engineer who can build algorithms which are practically fast enough to be used in real life, you watch the video till the end and you may decide for yourself. So let us understand the k-means algorithm first. So the k-means clustering algorithm is a popular unsupervised learning algorithm used for partitioning data into distinct groups or clusters based upon their similarities. For example, you want to cluster similar users in a social media platform, or you want to cluster similar images or videos. So let's see a really simple example and try to understand this. So this is our data, where imagine that each point here represents a smartphone. Okay, here we can see that the really cheap smartphones have really low rating, maybe because they're bad performance, and the average price smartphones had good features and are value for money, so that is why they have some good ratings over here. And the high price smartphones have also really low rating because maybe they are overpriced. Usually the rating of flagships are good, but for this scenario just imagine this, that it is low. Mainly because I've taken this example from the k-means visualizer created by Naftali Harris, which will help us to visualize this in just a minute. Here every smartphone is represented by two features, which is their price and their corresponding rating. So the smartphone S has a price, let's say $300, and a rating of 4.5 star. So the coordinates of this smartphone, the x-axis or axis 0 is 300 and the y-axis or axis 1 is 4.5. Okay, like this every smartphone will have their own two coordinates, which will be price and rating. Okay, so because we have two features, we have two corresponding coordinates, and because we have two coordinates, so we can say that the data is two-dimensional. If we had 3 features, then the data would be 3-dimensional. If we had 10 features, then the data would be 10-dimensional. Like that, we can have 100, 200 features and 100, 200 dimensions. It is common for a product to have multiple features, right? But at least for k-means algorithm and other algorithms that I know of, like gradient descent and forward propagation of a neural network, for us to write vectorized and efficient code using math, we do not require to imagine beyond 3 dimensions. If you have encountered any such scenarios, do let me know in the comments below. We will visualize and understand in just a moment, so watch till the end of the video. Coming back to the problem, we can see that the information about the smartphone is stored in a 2D array where each row represents a smartphone, and in total we have n smartphones. Because the example is really simple, we can see that here are 3 clusters, cluster 1, cluster 2 and cluster 3, and every cluster will have the center points. Like here we will have center point 1, here we will have center point 2, here we will have center point 3, like that. Okay, and to find these cluster centroids, we use the k-means clustering algorithm. Step 1. We need to select in how many parts do we want to divide our dataset into. Here, because the graph is 2D, we can see that there are 3 distinct clusters, so we can choose k equals to 3. But in real world situation, we choose k according to our business needs. For example, imagine that this is a dataset for various t-shirt sizes and you want to cluster the dataset into 5 parts, that is extra small, small, medium, large and extra large, and then you run k-means algorithm to find out the ideal values of small, medium, large, so that you can make good decisions while manufacturing. Here we want to divide our dataset into cheap smartphones, medium range smartphones and expensive smartphones, so that is why we will choose k equals to 3. Step 2. Because we have decided to divide our dataset into 3 parts, we will initialize 3 random centroids in our dataset, like this, this and this. You see the location of these 3 centroids are randomly initialized. Now we need to arrange them in the proper positions. So then we move on to step 3. We assign each point here to their closest centroid point. Here you can see this point is closest to the blue centroid, this point is closest to the green centroid, this point is also closest to the green centroid, and this point is closest to the red centroid. By the color of the area, we can see then which point is closest to which centroid. How do we find the distance? When we select one point here, like this, we will calculate the distance between each and every data point with each and every cluster centroid, and then we will assign this point to its closest cluster centroid. Here you can see the closest cluster centroid is blue, so this point is assigned to blue. So while measuring the distance, we usually take the Euclidean distance which we learn in our high school, but we are also open to take cosine similarity or Manhattan distance if we want to based upon our needs. Feel free to search it up on ChatGPT or Gemini. Step 4. We will calculate the average of all these data points assigned to blue cluster. Maybe it is somewhere here, and then we will relocate this centroid to here. Same we will do for green as well as blue centroids. Let's run it. Let's see what happens. You can see these points are assigned to blue, and we will upgrade the centroids here. So this was the average point of the green clusters here and here. So the centroid was relocated from here to here. This was the average point of the blue cluster, which is here and here. So the centroid was relocated from here to here. And same goes for red, and not much change in the red cluster. Now we will repeat the process and see what happens. You see it has gotten better. And now if I repeat the process again and again, you see not much change happens here. So this phenomena is called convergence. So we need to repeat this process until there are not much movement of the centroids, or in a formal way you can say that repeat until convergence. Okay, let's see a few more examples. Let's see with this. I will add 1, 2, 3, 4, 5 centroids, and I will repeat this. Let's see what happens. You see the process is repeating again and again, and it is dividing the cluster into 1, 2, 3, 4, 5 points. Okay, now I guess convergence has occurred. Let us add one more centroid point, and let's again repeat the process. This is so cool, right? So you can see that we have created 5 clusters. You can try it on your own. I'll give the link to this in the description. It's cool, right? So this is the brute force approach to find out the cluster centroid for each point in the dataset. Like if you have 500 points in your dataset, like 500 smartphones, this will go to each point, and then it will try to find and assign the closest centroid here. Even though how we find out the distance is vectorized and taking a time complexity of O of 1, but the entire implementation is taking a time complexity of kn, where k is the number of centroids and n is the number of data points is there. So before jumping into the vectorized approach and making this algorithm around 120 to 125 times faster, let us try to understand what is the problem with this approach, and with that we will understand what vectorization is, and maybe you will also understand that why GPU is so hit nowadays. Here let's say that you have 400 points and you want to divide these 400 points into 10 clusters here. Here each point and cluster is 3-dimensional. That means it has x, y and z coordinates, and the distance between 2 points is measured by this formula, which is distance equals to root over of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. You remember the third step. For every data point here, we calculate which is the closest centroid from each and every data point, and then we assign this point to its closest centroid. But the problem here is, if we see just one example from here, in order to assign this to its closest centroid, we need to calculate the distance between P2 and centroid 1, P2 and centroid 2, P2 and centroid 3, and like that all the 10 centroid points. Then we can calculate that which distance is minimum, that means which centroid is the closest to point P2, and then assign point P2 to that closest centroid. And we need to repeat this process for all 400 points. But the really big problem is, you just think that the operation where you calculate the distance between P2 and C1, is this operation dependent upon any other operation in your program? The answer is no, because to calculate D1 you don't need the value of D10 or D3 or any other thing. You just need these 2 points, P2 and C1, and then you can calculate the distance. So tell me, why would we calculate the distance D1, D2, D3 till D10 one by one? We can calculate all these distances simultaneously, right? Our computer can handle multiple tasks at a time, right? So why not calculate these distances parallelly and then see that which distance is the minimum? So these operations can be vectorized, or which means that these operations can be done parallelly, independent of each other. Similarly, all the operation in P1, P2, P3, P4 till P400 is also independent of each other. P1 does not depend upon P2 to find out its closest centroid, does it? It does not, right? So all these calculations can also be done parallelly. So why P2 should wait for P1 to get completed? It can do all the tasks parallelly, right? So does that mean we can vectorize these operations as well? Absolutely, we can. And how we can do this? With the help of math. Now let us understand the mathematical concept, and then we will implement the mathematical concept with the help of Numpy broadcasting. So before going there, for people who do not know what multithreading is, so threads are the smallest computational unit of our GPU or CPU of our computer, and each thread is capable of performing one small task. So you can imagine it like this, that this task is assigned to this thread, this task is assigned to this thread, this task is assigned to this thread, and so on. So these threads can perform the task parallelly, independent of each other, and hence doing the task in a lot faster time. You may have heard of multi-threaded applications. If you haven't, then this is the concept. If our CPU has thousands of threads, our GPU or graphical processing unit has billions of threads. You know what that means? That means you can do billions of independent tasks parallelly. Okay, the advanced deep learning algorithms are really heavy computationally, but thankfully they have a lots of independent operations like this. Like every neuron in the single layer of a neural network is independent of each other. Some operations cannot be vectorized. Like every layer in the neural network is dependent upon its previous layers. So we need to carry out the operation sequentially here. So although we can vectorize each layer of a neural network, we need to go through each layer one by one. And now we will understand how the math works. So this portion of the video may seem a little confusing at first. You may wonder why we are doing certain things, and it is absolutely justified from your point of view. But I promise you that everything is going to make sense at the end. So let's begin. So step 1 of choosing the number of clusters and step 2 of selecting centroids randomly will stay the same. We will work on step 3 and 4, where we want to find the closest centroid from every point here simultaneously, like this, and also move these centroids simultaneously like this. So in our 3D space, this is our x-axis, this is our y-axis, and this is our z-axis. So in the dataset we have 400 data points starting from P0 to P399, where each point has 3 coordinates, which are x coordinate, y coordinate, and z coordinate. Okay, and it is a 2D array, so that is why the shape is 400 by 3, where there are 400 points and every point has 3 coordinates. Now we will take 3 centroids, C0, C1 and C2. Here also each centroid has 3 coordinates. So here we can see in terms of programming that points as well as centroids are represented as a 2D array. And now first we will need to convert this 2D array to a 3D array. So this is our original array, where in the x-axis we can see we have 400 points and in the y-axis we can see we have 3 points. We will transform the array to have an additional axis and shift the y-axis to the z-axis, which visually will look something like this. Similarly, we will transform our centroids array and add an additional axis right here, which will look something like this. So now when we do points matrix minus centroid matrix, we get a resultant matrix of the shape 400 by 3 by 3, which looks something like this. You see each cell here corresponds to the subtraction of a point minus a centroid. Like here we have point 1 minus centroid 0. When we do P1 minus C0, it subtracts the corresponding value, which will give us a resultant value of this, where this corresponds to x1 minus x0, y1 minus y0, and z1 minus z0, which looks something like this. We have found very important piece of the puzzle here. Here we can see each of these values are used to calculate the distance between P1 and C0. Now we will take the square of 8 minus 3 and 5, and then we will add all of those together to get this value here. And then we will take the root of the sum to get the distance between point 1 and centroid 0. And because all these values are squared, summed, and taken square root to get a single number, so then this 3D matrix will get converted to a 2D matrix like this. So this is the distance between point 1 and centroid 0, and point 1 and centroid 1, and point 1 and centroid 2. You see the calculation that we did for finding out the distance between each point is completely independent. So all these distances In total 1200 distances are all calculated simultaneously. And now, to assign each point to its closest centroid, we can just see along y-axis and see which distance is the minimum and then assign that centroid to each corresponding point. For example, suppose the distance between P1 and C1 is the minimum. We can assign point P1 to centroid C1. And you also see one thing. Finding out minimum in each column is also independent of each other. So we can assign the corresponding centroids simultaneously. Can you imagine? All these assignments can be done simultaneously. Now we just need to shift the centroids and repeat the process until convergence. So this was the math. What do you think about this? I remember it blew my mind when I was actually able to visualize what was going on. So I decided to share this with you, and why not blow your mind as well. So let's see the code. It is really simple now. So here the function, find closest centroid vectorized. So here in the points matrix we are adding an axis here. In the centroid matrix we are also adding an axis here. We are subtracting the points matrix minus centroids matrix. We are then squaring it along the z-axis, and then we are taking the sum of it, and then we are taking the square root of it. So this distances is a 2D matrix whose rows are equals to the number of points and columns are equals to the number of centroids. And then we are looking the minimum distance or finding out the closest centroid and assigning them along the y-axis or axis 1. So compare these two lines of code to all the thing you have written here, and this will run more than 120 times faster with my CPU. I don't even know how fast it will get when we use GPUs and scale this to big data. Shall we see this running right now? It will take 30 seconds to see how image compression is done. So let us see that first. So this picture of this legend is 255 pixel by 255 pixel. So total we have around 65,000 pixels. Here each of this pixel can be considered as a point, where each point has 3 values or 3 features, which are red, green and blue, which corresponds to a single color. So I guess if there are 65,000 pixels, so there should be 65,000 colors in the picture. Yeah, I mean it makes sense. 65,000 pixels, each pixel corresponds to one color, so there should be 65,000 colors. But here you can see that some colors are too similar to each other to be stored as a different color. But the image extensions like PNGs and JPGs are already optimized, so they don't have 65,000 colors for 65,000 pixels. So for now, let us just assume that there are 65,000 colors. Here some colors may be repeating. We are ignoring that for now. So we are dividing or clustering these 65,000 pixels or 65,000 colors into 16 clusters or 16 colors. So when we get these 16 colors or 16 cluster centroids, we will go to each pixel and assign it to its closest centroid or closest color. So the initial size is 255 into 255, which is around 65,000 pixels, and each pixels has 3 values, red, green and blue. Each values are integer, and let's suppose that each integer is taking 4 bytes. It's around 780 KB. So for the final size, we still have around 65,000 pixels, that is constant, but each pixel will act as a pointer to 16 colors, where each color has 3 values that takes 4 bytes. So the size has reduced from 780 kilobytes to 65 kilobytes. Let's run this now. I have uploaded all the materials and code on Replit. You can run this directly from your browser. You'll have to just click the link in the description, fork this repository and simply just press run. So the default password is Replit, REPLIT, and you can run the code from here. So this was it for today. So if you enjoyed the video, make sure to like, comment down your thoughts, and I'll see you with some really cool machine learning stuffs. Bye bye.